Hello guys, today we will learn how to approach first law questions by deriving expressions to apply to energy balances. Let's get started. First, let's look at the energy balance for open versus closed systems. For closed systems, the energy balance is change in internal energy plus potential plus kinetic energy is equal to heat plus work. For open systems, we need to account for flow work, internal energy, kinetic energy, and potential energy of both the inlet and outlet fluids. Thus, our energy balance becomes change in internal plus potential plus kinetic energy is equal to mass flow in times the enthalpy plus half the velocity squared plus the gravitational constant times the change in distance plus heat and work minus mass flow out times the enthalpy plus half the velocity squared plus the gravitational constant times the change in distance. Recall enthalpy, which is the total energy of the inlet or outlet streams associated with flow work and internal energy. Let's look at how to simplify these energy balances. When your process is adiabatic, you can automatically leave out the heat in your energy balance. In most cases, you can neglect potential and kinetic energy because most of the time your system does not move, only the contents move. If your container is rigid or the volume stays constant, you can neglect work in your energy balance. If your process is isothermal and you are working with an ideal gas, change in internal energy is zero. And lastly, if your open system has a steady state, then change in internal energy is zero. Let's simplify equations based on given criteria to help you with problems you might face. Based on your system and type of process, you can use specific formulas to calculate the work, heat, and internal energy of your system. First, let's look at the isothermal reversible expansion or compression of an ideal gas. Since this is a reversible process, we can use this work formula. We are working with an ideal gas, which allows us to use the ideal gas law, which we can rewrite in terms of volume. If we think about the expansion or compression process as an infinite amount of very small expansions or compressions, we can rewrite this into a differential formula. We can substitute this into the work formula and simplify it by cancelling the pressures out and reach this formula. We apply integration and take out all the constants, temperature, mole, and the gas constant. Then, if we apply integration from state 1 to 2, we get a log function. We can simplify this using the log rules. Since this process is isothermal, we know that change in internal energy is equal to zero, and thus, heat is equal to negative work. Heat can thus be calculated with the same formula, just in the negative. These two formulas can be useful to remember when calculating work and heat. Next, we look at a reversible adiabatic expansion or compression of an ideal gas with constant heat capacity. Of course, the first thing we can simplify is our energy balance, since heat is equal to zero. Again, we consider the process to occur as if an infinite amount of small processes are summed together. Thus, we change our energy balance to a differential energy balance. Let's consider the internal energy. We know that change in internal energy is equal to moles times the integral of CV dt. Thus, the differential element U is equal to moles times CV times dt. Next, we look at the differential element of work, which we get from our reversible formula. We substitute this into our energy balance. Then, we relate P, V, and T with the ideal gas law and write it as differential terms. We expand this by using the product rule, and then simplify to get the differential element of temperature alone. Which we then plug into the energy balance and take a few steps to simplify. By separating variables and integrating, we get a log function. We make our equation less complicated by setting the Cp over Cv equal to K. We use log rules to simplify this even further. The negative in the exponent allows us to switch V2 and V1 and simplify. We expand the log functions and then rewrite. From this, we reach a specific relationship. PV to the power K is constant, which is a specific kind of process called a polytropic process. A polytropic process is a process where P and V is related with the following formula. PV to the power N is constant, where P is pressure, V is volume, and N is the polytropic index, which determines the nature of the process. Adiabatic processes are special cases of polytropic processes where the polytropic index is Cp over Cv. Let's use this polytropic relationship to get the work. We look at our reversible formula. We plug in PV to the power of K equals constant into our formula. If we integrate, we can take the constants out and simplify to reach our final formula. Since this is an adiabatic process, the work is equal to the change in internal energy. And that's our first 4 formulas to help with first law problems. I hope this video helped you to understand these formulas and know when to apply them.